get started. Shikest seminar. Welcome to Shikest seminar. Today, speaker is Professor Young Ha from USA. Yeah, thank you. He will give a talk about black hole entropy from large gauge transformations. Please.
Thank you. I'm glad to be here to talk about my paper that I wrote about 2 years ago. So I had to study it as if it were somebody else's paper because I couldn't quite remember what I wrote. Many things I couldn't remember, so I had to really seriously study this. Hopefully, I did a good job. Hopefully. 또 이러네. 어때? Okay, so after this talk, I hope that you take away the following lessons or messages. Boundary dynamics associated with non-dirichlet conditions is important for black hole entropy and black hole information, etc., etc. Boundary degrees of freedom with large gauge symmetry are the microstates, and they are responsible for black hole entropy. And there is a unified view according to which black hole entropy is entanglement entropy in a thermodynamic setup. When black hole entropy can be viewed as another charge. Sometimes it's, I mean, there are many methods of obtaining black hole area law, but I guess this is more unified view. So first, I will talk about the relevance of gravity quantification for getting entropy, and then I will quickly review Wald entropy versus Gibbons-Hawking Euclidean action prescription. And if time remains, which I kind of doubt, then I will also briefly talk about bound solution and black hole information problem. If I can finish item 1 and 2, I'll be happy. The main reference for this talk is this one that I wrote a couple of years ago. Right? I will throw several more references, but this is the main reference for this talk. So why is gravity quantization relevant for entropy analysis? So I guess everybody in this room agrees that black hole entropy is tied with black hole information. I think it's pretty well known. And the proper framework for black hole information must be quantized gravity, and this will be clearer shortly. The difficulty in cracking black hole information paradox can be attributed to several factors. Black hole information, black hole entropy, and they are all related. One may attribute this difficulty to intricacies in quantizing gravity, given that quantized gravity must be a proper framework for tackling the paradox. So quantization is gravity is difficult, therefore understanding black hole information is difficult. Another factor is the enigma of identifying black hole microstates that are responsible for black hole entropy. And I'm talking about 4 items here, but they are all kind of interrelated. Still, another reason can be found in that the boundary dynamics was incompletely dealt with in the past, at least in my opinion. The computation of black hole entropy presented here pivots on the boundary dynamics. So overall, non-perturbative bounds physics as well as boundary dynamics is indispensable for proper understanding of black hole entropy and black hole information. I kind of doubt that I will have time to talk about bounds physics, but we'll see.
What do you mean by boundary? Horizon? What?
They're like a asymptotic boundary, like a boundary in ADS-CFT. Spatial infinity. So we claim and show that large gauge symmetry is responsible for black hole entropy. What is a large gauge symmetry anyway? We know that small gauge transformation are those approaching the identity at spatial infinity. This is the usual gauge symmetry. I mean, the gauge symmetry that everybody is familiar with, right? But the large gauge transformation or large gauge symmetry do not approach the infinity, identity at infinity, right? So, I mean, that's like by definition. So we usually consider the gauge transformation parameter, like psi, that dies out at infinity. Then the e to the, right? That the transformation itself becomes identity. When the parameter, gauge parameter psi dies out at infinity. But if it doesn't die out, then of course the transformation doesn't become infinity, it doesn't become identity, right? Something else. So if you heard of the term the asymptotic symmetry, then the large gauge symmetry must be smaller. It should be included in the asymptotic symmetry. So some of the statements in my talk, the large gauge symmetry can be replaced by asymptotic symmetry, but not everywhere. So the small gauge transformation is redundancy, as you know. I mean, you should gauge fix it, right? You should fix gauge away those freedom. But large gauge symmetry is not like redundancy. It's like more like a global symmetry. So if you transform large gauge transform a solution, then it gives a inequivalent solution. So if you have a vacuum and if you transform it, then you have an inequivalent vacuum, right? So technical for that is that large gauge symmetry or global symmetry is like a moduli. Huh? So it's a collection of inequivalent vacuum. So if you're curious about large gauge symmetry, here are those two papers that you can look up to study large gauge symmetry. So let's talk about quantization of gravity for a bit. And so what I'm going to claim is that although gravity is not renormalizable off shell, right? I mean the non-renormalizability of gravity, as you know, it's a off shell statement, right? So, but what's being shown is that if you consider renormalization of the physical states, then it can be renormalized. So it's still a big claim. It's a claim that I made. It does not contradictory to the well-known off-shell non-renormalizability of gravity because it's it's just on-shell renormalizability, right? So, but it's still a big claim. So if you want to check some of those results papers, here is the more or less complete list of my work over last like 10 years or so. So the statement that I'm making the previous year is based on those dozen papers. Okay, so you can if you want. A crucial initial step in gravity quantization involves gauge fixing and handling of constraints. Probably if you study like literature on quantum gravity, quantization of gravity, probably you know what I mean, right? So constraints, it's a headache, big headache. And since a gravity system is a gauge system, its quantization can be dealt with in part by Dirac's method, Dirac brackets. I mean, it's not a bra and cat. It's not that that's elementary. Like a quantum mechanics bracket, it's more advanced. Formally, it's by Dirac, and it goes under the name of Dirac brackets as well. So according to this method, the second class constraints can be formulated by Dirac brackets. So there is a first class constraint, there's a second class constraint. second class constraint is, they are not a big deal. They can be dealt with according to Dirac's method, right? So it's not a big deal. What's difficult is the first class constraints, huh? So, but if you read the book by Weinberg, Quantum Field Theory, probably volume 1, I think, right? And there's a statement that you can fix that second, you can use up, you can use up that symmetry. You can take care of the second class constraint by fixing the gauge symmetry generated by the second class constraint. So second class constraint is basically like a residual symmetry, essentially, right? So you can fix it. If you fix it, you took care of it, right? So, and this has been demonstrated in my papers, right? His statement, right? So the first class constraint can be taken care of by fixing the gauge symmetry that it generates. This is a statement in Weinberg's book. In my papers, I demonstrated it using explicit examples. More specifically, the following was done in the Lagrangian ADM formalism, right? So I guess some of the students here do not know ADM formalism. It's a bit unfortunate. I mean, the talk I gave at Busan, it was pretty understandable and elementary, but this topic, I cannot make it too elementary. There are certain things that you should know as a prerequisite to understand the talk. So anyway, Lagrangian ADM formalism, and then with the lapse function and shift vector non-dynamical. So part of the metric, and they are non-dynamical. Right? They don't evolve. So their field equations were imposed as constraints upon gauge fixing the lapse function and shift vector. So they are non-dynamical. So their field equation is like a constraint. Huh? Okay. So and then this was in addition to the bulk gauge fixing. So if you read the literature on gravity concentration, like old literature, you impose like harmonic gauge or Didanda gauge, they're the same. I mean, it's just different name. So in QED, you impose like a Lorentz gauge and stuff, right? So it's just something analogous. In gravity, the most standard gauge is Didanda or harmonic gauge. It's very, very dominant gauge choice. This is bulk gauge fixing. So even if you impose this bulk gauge fixing, there is a residual symmetry. Okay, so you have to fix those residual symmetries as well. The symmetries generated by first class constraints. Because essentially the lapse field equation, the counterpart of the Hamiltonian constraint in ADM Hamiltonian formalism. So I'm using ADM Lagrangian formalism. More standard is ADM Hamiltonian formalism. And there is this constraint called Hamiltonian constraint. It's very, very standard in this literature, ADM Hamiltonian formalism, right? So, and there is a momentum constraint. So Hamiltonian constraint and momentum constraint, the standard ADM Hamiltonian formalism. I'm using ADM Lagrangian, but there's a map, there's an analog, right? So I'm talking about this lapse, basically lapse field equation in Lagrangian formalism as a constraint. That's analogous to a Hamiltonian constraint in Hamiltonian ADM. So anyway, that's the difficult kind of constraint because it's a first class constraint, I think, if I remember correctly. So yeah, so people have been trying to solve this constraint in the Hamiltonian formalism, first class constraint. No success for many years, right? Many decades, I would say, right? So, but then my proposal is that, well, we can fix that symmetry generated by that first class constraint. So if you do that, then one can show that the physical states, in other words, the states that satisfy this constraint is given by this, right? So I will come back to this a bit later. Right, so that was like an ADM formalism. It's easier to see this in the ADM, but as you know, ADM is like it's not fully covariant formalism, right? It's a 3+1 splitting formalism, right? So, but one can do this. One can achieve basically the same thing. In other words, this reduction of physical states, this one, covariantly. So it has been done, so it can be done. So, right. So these are the two references. If you're curious, that you can read to understand this.
So in that case, we can solve the first place constraint.
Yeah. So this picture, right? This reduction of physical states is actually these two works. These are the two of the dozen paper that I showed a while ago. This long list of papers, right? So two of them. There's actually two of Witten's paper written like several years ago. This and this that has some overlap with this with my papers. So I invite you to check yourselves.
So what about momentum?
Momentum constraint is also solved in my paper. It's not a big deal. It's and it has a certain implication, but what is really important is the Hamiltonian constraint or Leff's function constraint. That's the difficult one that people struggled with for many years. Okay, so this is the outcome of the solving the constraint. So normally, before solving the constraint, this is a bulk Feynman diagram, right? So you have this 4-point function, and the states here can be anything, can be the gauge degrees of freedom. It's completely off-shell, right? So you can put anything there, right? You don't worry about the physical states, etc., etc. You just put anything you want, huh? You can even put the gauge degree of freedom. So if you try to renormalize such a system, you know that it doesn't work, right? That's the statement of non-renormalizability of gravity. But if you restrict your physical states so that they have support on the 3D surface asymptotic boundary, like R infinity, right? 2-dimension plus time, so it's a 3D. So if your state has a 3D support, this is often called holographic screen. Then there's a sense of renormalizability that one can achieve. So anyway, with this, I hope that the boundary degrees of freedom is important, right? And because this is like a boundary, huh? This is like an asymptotic boundary. So, and then they are relevant when you try to calculate the entropy of a black hole, for example, right? So, so the lesson of the section 1 is that boundary degrees of freedom and boundary entropy, they are important. I'd say so far it's been kind of neglected, right?
What is the reason for existing or boundary degrees of freedom?
It's basically the large gauge transformation, right?
In non-convex diffusion movie, so you can eliminate by fixing the gauge.
Right.
Degrees of freedom.
Right.
Eliminate it.
Right. So So the small gauge transformation is a redundancy. You want to eliminate it, right?
In diffusion, is there any large gauge transform?
Yeah, right. The one that does not die out at infinity. And there was a statement, right? Is that if your transformation, well, let's think in terms of gauge parameter psi.
In gauge theory, actually, it has something to do with the large gauge transformation. Topological.
Right. So those transformation you don't fix, right? Because they're like moduli. They give you inequivalent vacuum, right?
What is the reason why?
Because it's like a global symmetry.
Global symmetry.
Right. Global symmetry is you don't gauge fix global symmetry, right? Because global symmetry gives you inequivalent vacuum. I mean, the good reference is this one, this two. Okay, so if you read those papers, you'll have a good idea what they are. Okay, so this is the core of the talk. And there are many like twists and turns. So I hope that you stay alert, right? So far it's like a preliminary kind of stuff. So this is the core of the talk. So we'll talk about Wald entropy and Gibbons-Hawking Euclidean action method, and another method. So apparently we are jiggling with 2 or 3 different methods of entropy, black hole entropy computation. But at the end, I hope to convince you that there is a unified view of all these apparently different looking methods. Right. So I'll quickly review. Wald, and then I will quickly remind you of the Euclidean action method, Hawking-Horowitz, Gibbons-Hawking, and Hawking-Horowitz, and this is the central result, provide a unified and generalized view of the black hole entropy. Wald's procedure can be viewed as a special case of entanglement entropy computation in a thermal or Euclidean setup. For a generic time-dependent solution, one should employ Euclidean action method. So Euclidean action method is the most general kind of technique. And then by computing entanglement entropy in this setup, one can kind of see that the Wald's entropy is like just like a show up, like So okay, let me quickly review. So if you know this Wald procedure, then if you don't, I guess probably it would be hard to understand what I wrote here. So, but for those who know, familiar with the Wald procedure, so recall how the area law is reproduced in Wald's approach. So you consider Einstein-Hilbert action, which is important. So you just consider Einstein-Hilbert action without considering York-Gibbons-Hawking boundary term, okay? So according to some author, which I forgot to put the reference of, if you consider only the Einstein-Hilbert action, you call that Neumann action. It's a kind of Neumann action. I think there are some different definitions, different kind of Neumann action, but this is just Einstein-Hilbert action itself is like a Neumann action, which I adopt. So I will call that Neumann action. So anyway, you take the variation, arbitrary variation, and then later you set this parameter. So you narrow down to the gauge variation, and then you do what you have to do. So and then one gets this expression, this variation of Ricci tensor, and then it's given by divergence of V law, where V mu is given by this, and then there is this identity that one can prove. You use this, and then one can show that the V is given by this, and then you substitute this back to the variation, and
How to express the large gauge transform?
that's common. Here it's here at this point it's like just usual small gauge transformation, right? And then later we'll think about large gauge transformation, and it's actually kind of subtle. So at some point here, even in Wald's derivation, you replace this parameter by Killing vector. Is Killing vector large or small? I think it's large, right? So, but he anyway considered without even mentioning it, right? Killing vector is like it doesn't die out, but anyway. So and then one can show that one gets this, and then this is you apply Stokes theorem one more time, then you get this. So Wald's definition of charge is this part, right? So it's a charge, and then there's a 2D surface, and then one can see that at this point, well, it's not clear what this quantity is, but then you have to replace this arbitrary gauge parameter by.
Killing symmetry is large gauge transformation.
If you ask me, I think so, but I don't know whether people.
You already mentioned.
Huh?
You already mentioned that.
Yeah, that's my opinion, but people just talk about killing symmetry without mentioning whether it's a small or large. They treat it just like just regular gauge symmetry. But it's not small, right?
Large means it depends on the boundary.
Large means that the parameter doesn't go to zero, especially infinity.
Killing vector.
Right.
Something to do with the boundary condition. In that sense, you are talking about large gauge transform. All right.
Killing vector K doesn't become zero at spatial infinity. That's why I think it's a large gauge.
Gauge theory, large gauge transformation means you literally change the configuration at infinity, finite amount.
Yeah. Yeah.
But here it's a killing vector. Killing
Yeah, so
vector
just-
does not change metric.
Right. So it's a symmetry. It's a special kind of symmetry. It doesn't change metric, right? But does it mean that it's small? Well, for us, it's not that important yet. Okay, whether it's large or small. I think if you ask me, I think it's a large gauge transformation. But,
If you have something else rather than metric, like scalar field one, then this killing vector rederivative can give you finite change at infinity. For metric itself,
yeah, killing vector doesn't change metric. Yeah, that's for sure. So anyway, let me move on.
the previous page you had a Rinsky curvature. Where is it now?
Yeah.
The last line. Last line.
Yeah.
Yeah.
For Schwarzschild background, this is zero, right? So yeah, I mean, I'm considering Schwarzschild. I think that's what Wall considered, huh? Schwarzschild background.
So diffusion is a gauge variation. Huh?
Yeah.
And then you consider isometry. So
Yeah.
it means
Killing vector.
just restrict the gauge group, gauge
Yeah.
symmetry.
Right.
All right.
Yeah.
Then
I mean, that's what he did, not me, but Wall.
okay.
Yeah, I'm just reviewing.
Okay.
This is a standard stuff. This is not me. Okay, this is Wall. Right. So then we replace psi by k, and then you evaluate this quantity here, right? And then we can use this identity that one can prove, and then you can compute. One can show that this gives you area law of black hole. Okay, this is wall stuff. Okay, everything. Right. So this is well known, right? It's very famous paper, right? But not is all well, as some of you tried to ask. Okay, the Wall's approach did not address the integration range of the action and overall normalization of another charge. So he defined this another charge with certain normalization factor in front, right? He just chose it. Of course, the value of black hole entropy depends on what normalization you choose. Yes, but he chose some value so that the charge integrated over the surface gives you black hole area law. And he also mentioned this interior boundary, which is what I'm talking about. You have the integral range. So with some at some point his integral range is from event horizon to infinity. There's no contribution at infinity. It's only event horizon. And he called it interior boundary, and later he identified it as event horizon. But that procedure is not clear. It's not clear to me at least, right? Right, but I will try to argue that with this unified view, right, which means that the entanglement entropy computation procedure, these two problems are naturally built in, right? It's not arbitrary choice, but they just naturally arise. Another unclear feature is that the starting point is, this is the point that I raised before, right? Neumann action, right? Discussed in the, I will define this next slide. because he didn't consider boundary, this Gibbons-Hawking boundary term. So without it, it's a Neumann, we call it Neumann action. With it, you call it Dirichlet action. But it's elementary, like a mechanics stuff, right? Your graduate mechanics course, that when you define charge, you use Dirichlet boundary condition. Okay, but he's defining a charge, but he didn't consider Yoke Gibbons-Hawking boundary condition. He didn't put the term, the boundary term, Gibbons-Hawking Yoke boundary term. He didn't do that, so it's not clear. One may also wonder why one must set the gauge parameter to Killing vector to compute the entropy. This part is understandable. The answer lies in the conservation requirement of a charge. So, to compute a charge, you need a conservation law, so which is provided by like a Killing vector. So it's not too bad. Right. So same story. Right. So, there's a whole issues regarding Dirichlet and Neumann boundary conditions. Once you define a charge with a proper Dirichlet boundary condition, then one may consider like a non-killing kind of vector for the psi. I'll come back to this later. Psi. Then maybe such a solution, such a charge, quote unquote charge, may represent some kind of leaking charge or leaking configuration, right? So I mean, if psi is not k, but some psi, some arbitrary, like a large gauge parameter, so then what is the thing that you are computing? The charge integrated over 2D surface, right? Where psi is not k, psi is just psi, large gauge transformation parameter. What's the thing that you are computing, right? So there are a whole bunch of questions, I think. Right, so to examine things more systematically, let's step back and let's consider this Euclidean formulation by Gibbons-Hawking. And then they put this proper boundary condition right here. So that's Gibbons-Hawking boundary condition. So the definition, my term, is actually another guy's paper. This is a Greek researcher. So he defined this Einstein-Hilbert action as Neumann action, and then with the boundary term, he called it Dirichlet. And then this is in 4D, Neumann action amounts to not adding, right. So, and we know that this is a thermodynamic, the standard thermodynamic stuff, where F is the free energy. Right, so they wrote this paper, very famous paper, and then they computed entropy in this setup, and then they found the area law again. So in their analysis, entropy basically comes from the boundary term. Okay, so this is a Euclidean description, right? So this I think is the most general kind of formulation. Now, what we are going to do is to like entanglement entropy computation in the setup. So okay, so this is like a third method, right? So first is the wall, second is Gibbons-Horowitz, and then this is the third one that I propose. And at the end, I will try to argue that they are like all like same. There's a unified view of all those three methods. So for entanglement entropy computation of black hole, which is, you'll see, is related to Wald's entropy, we divide the black hole into two regions. This is like a standard material, right? You have a black hole and then outside, right? And then you try to integrate out the inside of the black hole, right? And strictly speaking, it should be the degree of freedom associated with the stretched horizon, yes? And then it should this one?
I think that they obtain the partition function from the passage of in Euclid. Actually, they obtain partition function from the Euclid passage.
Right. Yeah, partition function is the exponential of this one, right? So in the exponent is F, the free energy. So that's partition function.
To be obtained from Euclidean action.
Right. 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 Right.
So S PH instead of Euclidean action.
I meant it's a thermal action. Isn't it the same?
When you think about the black hole system, then it could be someone, but yeah, it's Euclidean action.
Right. But I think in their paper they mention thermal action.
Right. TH should be entropy, thermal entropy.
Quantity.
Yeah. Thermal entropy. Yes. Yeah. All right. Because I'm running out of time, I guess. So I have to. Okay. So first step you try to trace out the inside, right? And which is supposed to give you a reduced density matrix, the entanglement entropy computation about delicate conceptual issues, as we will discuss now. So this computation is, of course, a highly difficult computation, right? So you have this thermal system, you integrate out the interior of a black hole. There's a technique called like a replica technique, but this is very complicated computation. I don't think anybody succeeded. So in principle, there are things that one can do, but it's a difficult, kind of computation. But here I'm gonna make a big jump, right? So hopefully you believe it or you convinced it. So if you this is a difficult calculation. So if one seeks the maximum value of the entanglement entropy, the general result employed above applies here. I will point out what I mean by this as well. So the maximum value will occur when the reduced density matrix takes the thermal form. So if you look up the book by Sakurai, quantum mechanics, right? So you start with this statistical definition of entropy. And then with some constraint, this constraint, this is constraint, right? And then you find the maximum kind of density matrix by taking variation, right? And then after some argument, some analysis, one can show that the maximum entropy results when the rho, rho takes the thermal form, e to the h, right? E to the beta h, I guess, is right. Right. So this procedure, I think it should apply even if you consider this calculation, reduced density matrix calculation. I don't see anything go different, right? So it's a very difficult calculation, but if you are interested in the maximum value, just like you are here, then again, the maximum entropy should occur when this reduced density matrix should takes a thermal form. This room is air conditioning is working, right? I guess it's just me who. Right, so there's a big jump here. It's a big conceptual jump. Maybe this is a weak point of the talk. I don't know. To me, it seems pretty natural, but it's not a rigorous proof. So I will just assume this and move on. So, right. So this reduced density calculation is again gives you this result. Okay, if you're interested in the maximum entropy, and we are interested in maximum entropy configuration, right? So in particular, the leading term of the logarithm of partition function is again the action, right? Right. So in other words, f, the leading term of f is like action, classical action, right? So what's crucial is that now the integration range of the action is between the event horizon and infinity, because it's a reduced density matrix, right? We already integrated out the inside. So that makes the action ranging from the event horizon to infinity, not from 0 to infinity. So the range does no longer include the inside of the black hole, right? So that procedure is the procedure that again take care of this problem, right? This integration range. While, as far as I can see, he just fixed the range by hand. But if you go through this procedure, right, then that's how this event horizon become part of the integration range. Right, so right, so I will skip some of this part here. So consider this entanglement entropy computation. You integrate inside, so the range becomes from event horizon to asymptotic infinity. But we already know by discussing item 1, section 1, right? So physical degrees of freedom sits at the boundary, right? Asymptotic boundary. So the integration becomes integration over the boundary.
When
Yeah.
you think about the utility of the
Yeah.
but we do not consider inside or the available what allow the visions from the horizon to it's not consider inside of the black hole. And you think about the utility of the black hole.
Oh, that's well known.
Yes, very easily you could check very easily. You can write the Schubert black hole and consider that it's Euclidean. And inside part, there are two terms in negative. T is very simple. You think about that Schubert black hole system. T square could be T tau square.
Yeah.
The inside part, the first one could be changed. The second part could be changed. So we treat something easily. We could transfer something potential transformation from the black hole boundary to the infinity. That vision could be allowed when you think about that. So we don't worry about the inside part.
Is that relevant in the work of Gibbons and the Hawking and Horowitz?
I mean that when you think about that something Euclidean formalism,
Right.
black hole system, using formalism, and some part of it could be the something Euclidean formalism, and usually in the space time, about the space time, you don't need to worry about inside part, only available things from the boundary. Very easily you could check the vision.
Right, but when you compute the entanglement entropy, right? You don't just integrate over the degrees of freedom that are available, but also you imagine integrating out the hidden, like unavailable degrees of freedom, right?
So I think that there are a lot will be several or 3 or 4 methods to obtain the entropy. The Euclidean formalism has the kind of entropy. But if you use the default kind of method, then you consider the others.
All right. All right. All right. So, you're basically integrating over the. I think I was kind of lost. Right. So I'm gonna skip. Right. So let me skip this part and let me continue with this. This entanglement entropy stuff. Right. So here, well, what I'm trying to do is this is an action evaluation procedure, action integrated over from event horizon to infinity, right? Because this action is a part of free energy F. There's a leading term. So we are looking at the leading term of the entropy. Okay. Basically, that's what we are trying to do. And we consider this transformed solute metric, right? So this is a metric transformation in an active form. And then we consider Neumann boundary condition because we are imagining this this active gauge transformation act on the original solution. So once you consider active gauge transformation, the Dirichlet boundary condition is out of the window. It's a Neumann, right? Once you consider large gauge transformation, the boundary condition cannot be Dirichlet, should be Neumann. Right. So right, we consider Neumann action. So this is the action, the leading term of the free energy. Right, so our starting point is kind of similar. It's a gauge transformation, right? But in our case, the crucial new ingredients are boundary dynamics and large gauge symmetry, right? Also, the starting point is the entanglement entropy calculation, unlike the original wall derivation. So what I'm trying to show here is that for the Schwarzschild solution, the action that vanishes, right? Right, R vanishes, and then this part is basically what the wall's computation is about. This is the wall entropy. Schwarzschild, for Schwarzschild, this vanishes. You may ask, what about the solution like a curve, some other solution that doesn't have a vanishing action? It's discussed in my paper. It's not really difficult, but I don't think I have time to discuss that. So I will just focus on the Schwarzschild solution. Okay. Then, so for Schwarzschild solution, one can show, and I'm going to show you that this vanishes, and this is nothing but the wall or the wall's computed, the wall charge. Okay, integrated over 2D surface. This is this. So essentially, his result is this. That's why we have a unified view. His result is nothing but entanglement entropy computation in a thermal setup, right? So, but then this advantage of this setup is that you don't the normalization of the charge is naturally built in. The range, like inner boundary, naturally arises, right? So, okay. There are some delicate points. Let me see how many now. Okay. So as I expected, I don't have time for this, but hopefully I'll be able to finish this section too. Right. So there are certain concepts, subtle, delicate issues. For the reason to be explained, this gauge parameter will ultimately be taken to be killing vector, right? This large gauge transformation will set it to be killing at the end. It may appear that one should get 0 for variation of terms in the functional Taylor expansion, since the original configuration is invariant and the original value of the action is 0. So, right, so you consider this is so what I'm saying is that because this is a symmetry, this should vanish. That's what I'm trying to say, naively, huh? If this is a symmetry, right? Then symmetry of the action, if it is a gauge symmetry, then this should vanish. That's what you mean by symmetry, right? But that's naive because you have event horizon where there is a certain kind of singular coordinate singularity. Usually it's called coordinate singularity. What I'm saying is this: not coordinate singularity is not nothing. It has some physical meaning, I think. Right? That's part of the. So, however, this is not the case. The original configuration is invariant on the killing symmetry only outside of the black hole. At the event horizon, the crystal fault symbol becomes singular. Right? So there is some subtlety when you evaluate this action. Naively, you think you get 0. But then you are doing like, you have, the infinity at the event horizon, right? Right. So one should introduce certain regularization, actually. So the singularity at the event horizon is usually referred to as a coordinate singularity. All this means is that it is not a covered singularity. So I view the term coordinate singularity is misleading at the quantum level because, I think that there's this debate. I don't think this firewall puzzle, right? It's been settled entirely. Still, it's an ongoing thing. And there's a group of people who doesn't believe firewall. There's a group of people who believes in a firewall. So if there's a firewall, then of course the event horizon is not nothing. It's something, right? It's not coordinate singularity, but it's not nothing. It's just something. It has physical meaning. So that's this analysis seems to indicate as well. Right. So the metric should be viewed as a changing according to whatever is dictated by the actual form, the killing vector, in light of the singularity, this Stokes theorem, right? So I review the Stokes theorem. That procedure, you have to go through a similar procedure. It arises as a part of this analysis. Okay, it's basically saying the procedure, right? You have a different interpretation. But mathematical analysis is just it's basically the same. But then now you have to worry about the fact that you have a singularity at event horizon. Huh? Without that, you get zero. With it, you don't get zero, right? You have a black hole entropy. Without knowing it, one is introducing certain kind of regularization when you do the computation. So that's what I'm trying to say. So my stance on this matter is that the northern method is nothing but an evaluation of the action of the original solution, the solution before the killing transformation, even though it employs the killing transformed one. In other words, the northern method is a way of extracting a singular contribution from event horizon of the original action. The procedure must be computing this contribution through a certain stable regularization. I mean, you are implicitly you're using certain kind of regularization, right? The regularization is such that one may take the procedures right. So the regularization is such that it gives the area law. Okay, that's the regularization that you are implicitly using without maybe realizing it. All right. So this is one of the things that I mentioned before. So if you set this parameter to be a killing vector, then it's a Wald procedure. It's a part of the Wald procedure. It's a charge, and it's a symmetry, global symmetry. So that's that you should do that. But what about if you compute this for genetic data, just non-killing large gauge transformation parameter? What's the meaning of this thing? Oops. What's the meaning of this thing? This is a charge. Does it have a meaning? I mean, it's not even a Dirichlet boundary condition that you're dealing with because you're considering large gauge transformation. So perhaps my interpretation is that so it's not entirely clear what's being computed. What's that charge integrated over 2D surface? So the psi transform solution will not be an isolated system. If your boundary condition is not Dirichlet, your system is not isolated. Okay, and that's why you impose a Dirichlet boundary condition in the first place, to make the system isolated, right? But if you have a normal boundary condition, your system is not isolated. That means that something is leaking. So perhaps if you use generic large gauge transformation parameter, you're computing still the entropy of the black hole, but it's a leaking configuration. That's my proposal interpretation. Right. So the remaining is kind of technical, so I don't want to bother you with these technical details. The thing is that what I'm trying to show you is that, first of all, instead of variation, one can use this Lie derivative symbol. They are the same thing. Right? So variation is a Lie derivative. And then so the Taylor expansion here is this variation expansion. Here, this is like a first one Lie derivative here, plus the next order is a Lie derivative square, actinometric, etc. Right? So this part of the slide is that okay? So for Schwarzschild case, the leading action, the classical action is 0. The first correction, one derivative acting on action, that's world entropy. Here, what I'm showing is that this thing, the next order, right? Right, and more, right? These all vanish. Okay, so that's what I'm trying to show here. Right, but I don't want to go any detail of this procedure, so you can check my paper. There are some result that you have to use out of another paper of mine. You know, this relation, but that's just too technical. So let me just. So for to wrap up the talk in the next 5 minutes, I will just briefly mention this bound solution in black hole information. So what Hawking and his collaborators and many other people, what they consider in semi-classical analysis is basically this amplitude. The black hole here the 0 denotes a fixed geometry, because in semi-classical description you fix your geometry, right? So this is the amplitude basically they consider. Then you get information paradox, right? So, but what one should really consider is this is a black hole state, and then this M is not a mass, it's a Minkowski, right? After black hole evaporates, right? So it's a different solution of gravity theory. You should consider this kind of amplitude. So not just equivalent vacuum like this and this, same vacuum, but different solution. The transition between different solutions. Okay. So this notation is actually naive. This is not a precise notation. More precisely, you should consider this false vacuum. So initial collapsing solution, black hole collapsing solution, right? And then true vacuum is the wormhole solution, white hole. That's the final solution, right? So the amplitude that one should really consider is this type of amplitude, right? Not this kind. Not this kind. So this is semi-circumscription. This is the origin for the black hole information paradox, right? If once you do that, then you know, right, information is preserved. So, and then once you consider this, right, this, then this is basically the bound solution, right? Right. This means that your classical solution is a bound solution. So you consider this is one of the wormhole and black hole collapsing solution right here and here. And you put some correlator, right? And then you do all kind of contraction. At the end, you end up with this amplitude without this thing, right? They give you some extra factor in front, but you basically have this remaining, and this of course depends on your initial condition, right? So your result depends on your initial condition. So there's no information paradox, qualitatively, right? Qualitatively. And then yeah.
You have any reason to collapsing?
Any what?
Any reason to by collapsing the level and modeling the kind of things? Force vacuum state, it's not a pure black. So could you show that something that also the first and two
So
that the next time and force vacuum correspond to initial collapse. Initial collapse is not a black hole. So do you have any?
right, it's not a black hole, but when like this like a shock wave kind of thing, right? So I'm talking about that kind of solution, right? So usually we believe that leads to like a stationary, like a black hole if you wait long enough. But I guess what I'm trying to say is that that's your false vacuum, right? This collapsing shockwave collapsing solution is a false vacuum, and then black hole evaporating is like a white hole, right? So this is the true solution, right? So if you consider that configuration, that's what your bound solution represents. So, right, that's the vacuum. That's your vacuum. That's the vacuum that you consider to deal with the scattering process, for example, right? So if you do things in this setup, there is no information loss, right? Because your amplitude depends on the initial condition. So again, I think, in my opinion, what was missed is that people just consider in semi-scale approach this, right? If you fix the geometry, the boundary dynamics is also fixed, but they are the entropy. So you get rid of all the entropy by doing this. That's why you have information loss. Thank you.
Thank you for giving me that detail. Do you
It's still, I cannot understand how the large case transformation enter into your interpretation. What's that mean? Can you-
Oh, maybe okay, maybe I will. So maybe I will just give you new Takayagi. Where is it? Maybe that should help, right? Here. So there are like two ways of seeing how that boundary degrees of freedom enter. One way is to through new Takayagi. So consider a black hole and split the region, right, as usual, inside and outside, and you compute the entanglement entropy of black hole after tracing out the states inside with gauge fixing. So we as I explained in the part the section 1, gauge fixing, right, first class constraint gives you renders the physical state to be at the boundary, right? They have support at the boundary. So you are the remaining integration. You integrate out the inside. So you have integration over the rest, right? Over the rest means that from entropy to infinity, right? But according to what we find, if you fix the gauge symmetry completely, the physical degree of freedom has only boundary support. So basically, you're integrating the boundary over the boundary. That's how the boundary degrees of freedom become relevant, right? So so your integration range at the end is over the boundary. But when you try to evaluate this boundary integration, the non-zero contribution comes from event horizon. So this is like, so people in the past compute the entropy by analyzing the event horizon, right? So there's this tension. The entropy comes from event horizon or boundary. They are not contradictory. Your degrees of freedom sits in the boundary, right? Large gauge transformation. So when you try to evaluate that the integration, the zero contribution, a non-zero contribution comes from the event horizon. So anyway, that's one way to see the boundary degrees of freedom is relevant. So even more basic level, once you consider large gauge transformation, you have to consider boundary dynamics, right? Because large gauge transformation lives in the boundary.
I guess it's element, and when you compute entropy through some technical cases, right, by computing some variational action.
Right.
So where the large case transformation enter into the it's here that is and X. Yeah,
Here, right?
actually, I cannot see the difference with word formulation here.
So this here, this parameter is not small gauge parameter. It's a large gauge parameter. So large gauge transformation is entering here. Why we consider that? As I said, this
Actually, that I agree, but I mean, in the actual computation.
Right.
Actually, I cannot see the difference.
right. So the reduced density matrix, you integrated out inside the degrees of freedom. So you have remaining degrees of freedom from event horizon to infinity, right? But the physical degrees of freedom, all this inside from event horizon to infinity, except the infinity itself, they are like a gauge degrees of freedom. So you're integrating the whole thing, but at the end, you're integrating over the physical states. That's how it enters.
Okay, then I will consider small gauge transformation as usual. Then what's the difference between this?
Small gauge transformation, you don't have a good physical, you don't have good interpretation. I mean, like a Wall did, like, you can just do this, right? What Wall did. It's excellent work. I'm not criticizing, or anything, but this leaves a bunch of questions, right? So here, you may think that this is a small gauge parameter, right? He didn't mention it, so I assume that he believes that this is a small gauge parameter. But then there's a whole bunch of questions. He's considering Neumann action, right? Neumann action is for large gauge parameter. It's not for small. So you can do this, but you don't have good interpretation. You have a whole bunch of questions that you should.
Do you mean that the voice from lesson is already large gauge transformation?
What I'm trying to say is that I don't think he really understand all the questions that one is facing. He answers some good part of the questions, but not all. So to properly formulate what he did is basically one should employ the entanglement entropy formulation. With that formulation, what he did makes sense. It's a good interpretation. But without it, you don't know what he's doing. And basically, right. I mean, I don't know what he's doing.
You draw a curve in your data.
Right. So yes. Sure. It's in my paper. I'm not really prepared to talk about it. I kind of forgot everything about it. It's 2 years ago. Yeah. Yes. So in this picture, page curve very naturally arises, right? It's very generically arises. So it's not.
Or not?
It's the usual design, but I don't think it's exactly the shape that the page.
In the boundary.
Yeah.
From the boundary viewpoint, if you fix the, for example, the large transformation, everything should be constant forever.
No, because the black hole grows, right?
Yeah, but everything lives in the boundary. That means
No. Remember,
what?
your integration. No. Your integration. You're integrating over the boundary, but at the end, the non-zero contribution comes from the event horizon, and event horizon grows as black hole evaporates, right?
Yeah, but you told us that everything lives in the boundary.
But that does not contradict the fact that the non-zero contribution comes from the event horizon. It's in my paper, so you can just look it up. I'm not making it up. It's been considered. It's been addressed.